Hi everybody, today's video lecture is about solving some problems related to Galois correspondence. So these problems take place at the end of section 14.2 of Damit and Food's book. So I'll solve just some of them as samples. So let us begin with exercise 4 and 5, which are closely related. So let P be a prime. Okay, it says determine the elements of the Galois group of the polynomial x to the power p minus 2. I mean, this is intended to mean it's the splitting field of x to the p minus 2 over q. And exercise 5, let me continue here. Prove that the Galois group is isomorphic to the group of matrices let me say H equals, so these are 2 by 2, A, B, 0, 1, where A and B are in FP and A is non-zero. So A and B belong to the finite field with P elements. Therefore, I mean, it's easy to notice this is a finite group, and actually you can immediately count the number of elements. So show that this Galois group is isomorphic to this particular finite group. Okay, so let's proceed. First, the strategy will be to explicitly write down the elements and then to explicitly write down the map. Okay. Okay, first of all, our polynomial is x to the p minus 2, and its roots are the positive real p root of 2 along with all these zeta to the k times p root of 2, where zeta is just a primitive p root of unity, which we'll take here for concreteness 2 pi I e to the 2 pi I over p. Okay, and this immediately implies the splitting field of k over q, sorry, of this polynomial splitting field k of this polynomial x to the p minus 2 over q is simply q adjoint p root of 2 and zeta. This is simply because whenever you contain all these roots, you have to contain their ratios. Therefore, you have to contain p root of 2 and zeta. Conversely, once you contain these two elements, it's obvious that you contain all the roots. Therefore, this must be the splitting field. Now, how about its degree over q? This is something we talked about before at some point. Now, let's look at the following subfields. You have q p root of 2, and you have q zeta. Now, we know something about these degrees, right? So, first of all, the p root of 2 has minimal polynomial exactly x to the p minus 2. This polynomial is irreducible by Eisenstein's criterion or otherwise. Therefore, this degree here must be p. How about q zeta over q? The minimal polynomial of zeta over q is the pth cyclotomic polynomial, and when p is prime, this is a particularly simple form. It's x to the power p minus 1 over x minus 1, which is the sum of all these powers of x from the 0th power up to the p minus first power. Okay, so this is the minimal polynomial, so this degree is p minus 1. Now, p minus 1 and p are relatively prime, therefore we can complete the other degrees up here, and this altogether implies that this extension has degree p times p minus 1. Okay, now k over q is clearly a Galois extension, simply because k is the splitting field of something, and it's a separable polynomial, right? So if we set G to be the Galois group, then the order of G must be equal to this degree of this extension, which is p times p minus 1. So the group in question has order p times p minus 1. Okay. Now, how to identify its elements? Now, any element of G is determined by what it does on p root of 2 and zeta. And these should be sent to conjugates. Therefore, the possibilities, let's list them. At this point, we don't know if these can be mapped freely to wherever they can, but we'll find this out in a moment. This must go to one of the conjugates, and the conjugates are zeta to the a times p root of 2, where a is in the set. Therefore, you have p choices, and zeta should go to one of the conjugates. But what are the conjugates? It's zeta to the k. Now, k here must be relatively prime to p, but you know, p is prime, and that has a special role. So k should be in the set. Okay. Now, this is nice because there are a total of p times p minus 1 possibilities altogether. But p times p minus 1 is equal to the order of G. This means that all of these possibilities should be realized. Okay. Okay, therefore, we can almost list the elements of G now. Now let's try to define certain specific elements like generators. We have to be a little bit careful though. Now let's sigma send p root of 2 to zeta times p root of 2 and zeta to zeta. Okay. And let tau k, let's say, send p root of 2 to itself and zeta to the power k. I didn't want to just write a single thing here because, you know, there's a difference here. I mean, sigma generates some cyclic group, subgroup, right? So sigma squared up to sigma to the p minus 1, I guess. So these give you everything that doesn't move zeta but moves p root of 2 to one of its conjugates. But the same is not true for tau k, because depending on the number theoretic properties of p minus 1, you know, you might need more than one generator here. Okay. Now, but it's clear that every element of G can be written in the form sigma to the power, let's say, A times tau sub k for a unique A in 0, 1 up to p minus 1 and k in 1 up to p minus 1, sorry. Okay, so this gives a list of all the p times p minus 1 elements. Okay. Now, to be able to go on, maybe we have to write down the multiplication rule in terms of these generators. So what if you multiply two group elements like this? I mean, rewrite it again in this form. That would really describe you the group operation. So essentially, we have to know how to commute these middle elements, right? So look at this middle part, tau sub k1, sigma a2. In order to understand this element of the group, let's see how it acts on p root of 2 and on zeta. So first act on p root of 2. Well, at first stage, sigma to the a2 will take it to zeta to the power a2 times p root of 2. Now, if you apply tau k1, zeta to the a2 will go to zeta to the a2 times k1. And tau will not touch p root of 2. So this is what we have. Okay, now let's also look at the action on zeta. The sigma part doesn't change zeta, so this is equal to tau sub k1 zeta, which is zeta to the k1. Okay, now these two imply tau k1 sigma a2 equals, Okay, now which element does this? So let's look at it carefully. It must be tau sub k1 here again. But now sigma to the power a2 k1. So the expense of changing the places is changing the power of sigma to a2 k1. Okay, now if you just use associativity here, we can now understand this product, sigma to the a1, sigma a2 k1, tau sub k1, tau sub k2. But now it's easy to see that sigma to the a1 times sigma to the a2 k1 is just sigma to the a1 plus a2 k1. On the other hand, tau k1 composed with tau k2 is tau k1 times k2 because you are taking a second successive power of zeta. This is k1 times k2. This is the proper thing to put. So this is kind of the group law here. If you want to think about it as an abstract group, its elements are sigma to the a tau sub k, and the multiplication rule is this. Okay. Now, how about the isomorphism to this matrix group? Let's keep this relation here. Now, you have G, the Galois group, and also H. Let me recall what H was. It was AB01 such that AB are in FP and A is non-zero. I mean, let's write this isomorphism quite explicitly. It will take sigma to the A tau sub k to, okay, I mean, I have to be a little bit careful. So this k will go right here. Okay, this power A will go right here. 0, 1. Now I claim that this is an isomorphism of the mentioned groups. Now, it's kind of clear that phi is a bijection. I don't need to say too much about this because, I mean, just look at this. Tau sub k, this k, number k, was a number from 1 up to p minus 1, so you cover all the possibilities where k is non-zero here, and that's what you ask for. And likewise, for a, you can put here all the numbers from 0 up to p minus 1, and that covers all the possibilities for this corner. So it's clearly a bijection. The only thing to check is that phi is a group homomorphism. And for this, it's enough to check that the matrix multiplication rule agrees with what we found upstairs. So let us multiply k1, a1, 0, 1 with k2, a2, 0, 1. This is going to be k1 times k2 And here on this corner we have K1, A2 plus A1 and then 0, 1. Now, the whole point is that if this is phi of sigma to the A1 tau sub K1, so this should be sub, and if this is phi of sigma A2 tau sub K2, then, well, first of all, this is phi of sigma A1 plus Ka2 tau sub K1 K2, but this was exactly the group law in G, therefore this immediately shows that this is a group homomorphism and finishes the proof that this is an isomorphism between G and H. So that solves the problem. Okay, now let's pass to a completely new question. Okay, again, this is Damit and Food, section 14.2, exercise 8. Okay. The question is this: suppose K over F is a Galois extension of degree P to the N for some prime P, and some N at least 1. The question is, show that there are Galois extensions of F contained in K of degrees P and P to the power N minus 1. Okay, now we'll prove something a little bit stronger. Okay, let's keep the question a little bit more. Okay, now the fundamental fact is the Galois correspondence. So, by assumption, the Galois group K over F has order equal to the degree of the extension, which is equal to P to the N. So it's a P group. It's a finite P group. Now, there is something fundamental that the Galois correspondence says. By the Galois correspondence, the extensions that you're looking for, any Galois extension of F contained in K corresponds to a normal subgroup of G of the relevant order. So any Galois extension of F contained in K corresponds to a normal subgroup of G. Okay. Now, therefore, it's enough to show that this P group G has normal subgroups of order P and order P to the n minus 1, well, in a sense, reverse to this. For the degree P extension of F, you need you would need an index P subgroup and vice versa, but anyway, the numbers are symmetric. So G has normal subgroups of orders P and P to the n minus 1. Now, this is kind of a standard fact about P groups, but let me try to prove it anyway. So there's a stronger result, so more is true. So G has normal subgroups of order P to the K for any K between 1 and n minus 1. So all the intermediate orders as well. Let's prove this. First step for proving this is to show that the center of the P group is non-trivial. Why is this so? Well, you could write the class equation, which is just kind of grouping the elements of G according to the equivalence relation of being conjugates. So, well, if something is in the center, it's only conjugate to itself, and that's kind of an if and only if. So write those elements separately, and all the other conjugates classes as a separate thing. So okay. Now here xi's are representatives from each conjugates class such that xi is not in the center. So I mean, all the elements which have, you know, a non-trivial conjugate, you just write them in these groups. So well, what does this imply? But now here is where I use that G is a P group. P divides each of these indices because the centralizers are proper subgroups if xi is not in the center. Therefore, this group must have some order divisible by P, and also P divides the order of G, so this implies P must divide the order of the center. So the center is not trivial. But now the center is not trivial. It has an order divisible by P, so let me write this order. This must be P to the K for some K greater than or equal to 1, and obviously it's abelian, so ZG will have some subgroup of order P. subgroup H, let's say, of order P, which is obviously normal, in G because it's contained in the center, therefore elements of H commute with everything. Okay, so we show that G has a normal subgroup of order P. Well, what about the other orders for normal subgroups of order P to the K for other K? Do kind of an induction. Well, let me, without going into full detail, let me write the induction step. So G over H is now a normal subgroup, H is this order P group, has order 1 less than P to the power 1 less than the original order, so P to the power n minus 1. Therefore, by induction, G over G quotient H has normal subgroups of order P to the K for K between 1 and n minus 2. Now, pull all of these normal subgroups back by this natural epimorphism G to GH. I mean, pi inverse of these normal subgroups will be normal, and that produces you all these subgroups that you want. Okay, so that in particular proves that you have a normal subgroup of order P to the K for each K, and it also answers the question asked. Okay, now let's solve one more problem. Okay, this is exercise 11. Okay, the question is as follows. Say you have an irreducible quartic so degree 4 whose splitting field over Q has Galois group isomorphic to S4, the symmetric group over 4 letters. Okay. One might ask if you can find such irreducible quartics. Actually, this is kind of the generic case, but okay, let's assume this without proof for now. Okay, now let theta be a root of fx in some algebraic closure, or in C if you like, and set K to be Q theta. Okay. Prove that K over Q is an extension of degree 4 with no intermediate subfields. So there's nothing between K and Q. Okay. Now, the question has one more sentence in its statement, but let me skip that. Let's do this for now. Okay, now let us be careful. This Q theta is definitely not going to be the splitting field itself. This is just one root, but if you want to contain all the roots, you can get much more. And indeed, the assumption is that the Galois group is S4. So let's L be the splitting field of F over Q, then the order of the Galois group must be equal to the degree of the extension, but also we know that, we assume that this Galois group is S4, so this is the order of S4, which is 4 factorial, which is 24. So this is a degree 24 extension. So this K should sit somewhere in between L and Q then. Now, the degree of K over Q is 4 because of an easy fact. This is the degree of the minimal polynomial of theta, but that is F because F is irreducible to start with. Okay, so you have the splitting field is of degree 24 over Q, but K is degree 4 over Q. Okay, now in order to answer this question, let's just draw the lattices and use the Galois correspondence. Now, on the group side, you have S4 on top, and you have the trivial group on the bottom, and you have the subgroup of the lattice of subgroups here. Well, what about on that side? On top, corresponding to S4, the fixed field is Q, and on the bottom you have L. And from here to here, it is degree or order 24. Okay. Now, what about K? Well, K is sitting somewhere here, and we just said that this degree of this extension is 4. Therefore, K must correspond here to some subgroup, right? It must correspond to some subgroup of index 4 in S4. Now, here's how we can answer the problem now. If you had some intermediate field here, I don't know, let's say F, there is not too much option. Suppose there exists some F strictly between K and Q. Then, since this degree is 4, the only possibility is that these are 2 and 2, right? But then, corresponding to this F, you would need to have something between these two groups. And these relative indices here should be again 2 and 2. But okay, now we know one big fact. what is an index 2 subgroup of the symmetric group? You can easily show that there's only one possibility, and that's the alternating group, A4, which has 12 elements. But now you go back to the alternating group on 4 elements. So it should have a subgroup of index 2, but it does not. So A4 does not have a subgroup of index 2, which is a contradiction. So F doesn't exist. Okay, how can you prove that A4 doesn't have a subgroup of index 2? You can enumerate all the subgroups if you like, or you can show that if it had one, then you would have a surjection onto Z2, which is impossible by looking at the elements. And this finishes the group. This finishes the proof. Okay. Okay, so that's all for this lecture. Thank you very much.